introduce our today's speaker, and actually he is our former student. He graduated from our department in 2000, no, I'm wrong, in 1980. And worked at Science Application in Palo Alto for some time, as well as at Brookhaven National Laboratory until 1987. 1987, he went back to Korea and joined Korea Advanced Institute of Science and Technology, KAIST, where he has been involved in teaching and research in reactor physics and neutron transport, computational methods. 3 years ago, in September 2014, he became a professor emeritus, and he is now associate editor of Nuclear Science and Engineering Journal, as well as fellow of American Nuclear Society. So he will be giving a talk on one of my favorite topics from transport methods and neutron transport equation. So how many of you had 250? Okay, 255. Okay, so you will be able to follow what Professor Nam Zin Cho will be talking about today. And we are trying to convince him to write a book.
Okay, thanks, Jacobian. It's very nice to be back. I think last time I came here was 2011.
2000, yeah.
But before that, almost I came every other year. But since that, I a little bit relaxed. I left, as you mentioned, I left here about 37 years ago. It was a couple of years ago. We were overlapped. And it's always nice to be back. He reminds me, 250, 255, the same course number.
Same numbers.
Never change. And Jasmina asked me before I start this to say something about the status of nuclear power in Korea, because we have a new president about 4 months ago, I guess, 3 months ago, and he's from the I don't know whether I can use this word, left-wing ideology, at least the people behind him. And so he used to be a human rights activist. He is a lawyer, but now he's around by those people, and he doesn't really, to us, he really doesn't have really background in engineering or even politics. He's kind of new in politics. So people think that they are, I mean, he is being manipulated. No,
I will say manipulated.
It's too strong a word. But anyway, so he proposed to, actually he ordered the utility to stop the construction, two-unit construction, which the construction has been gone up to 30%, already 30%. He ordered to stop. And then he composed the committee of about 300 people. And then in 2 months debate, and from opposition side and also utility pro or nuclear side. And their mandate for this committee was whether or not we start this stopping of the construction 30% is already been done. And but that's a single item. It was a mandate. But at the end, last day or so, they add another item. They, by themselves, maybe not by themselves, but they add another item, which was with the new plans, site preparation. We have 6R on the plan. Two units are already site preparation has been gone, some percent. The other 4 are site selection has been done. So they add this additional item either by themselves or for some reason. They voted on two items. The first one, original one, was favor to restart the construction already being going on. But they voted on the second one, vote down, no new plans. So the debate was only on the first one because that was the only mandate for this committee. But last day they add this second one. So no discussion on this. So from these results, we are very concerned about this because it will be a long-term impact. So, but now the residents, the people around the site, the proposed sites, they are calling for building because the economy and all of this. So let's see what happens. So the crucial point will be who will be elected next as next president, which is 4.5 years.
4 years.
4 years later, yeah. So if the current party, the ruling party continues, then it will be very, very dim. The nuclear will be very dim. If it is reversed, then we'll keep on track again. And this is the time is very important because this is the time we may have opportunity to export power plants. Saudi Arabia, Czech, United Kingdom, and so forth. So for us, we have a supply chain intact at this point. But if we don't have new plants, then supply chain will also break down. So next election is very important, which is 4 years away. So let's see. For immediate concern for us, university, the students. So far, the student was flowing in, but let's see what happens. But other areas worse. I mean, the other engineering, the shipbuilding is gone. Right? So nuclear was really in the last several years. Nuclear was very promising, and a lot of students coming in. So under this new environment, let's see what. On this, any question? Well, let's. So this is the work I have been, or the students have been doing the last couple of years, which is to look at the transport equations everybody familiar with. Multigroup transport equations. So from the basic start, we are trying to write it down differently from the existing ones in the course. So I'll follow this basically. What's the problem or the limitations in conventional multigroup transport equations? of course, starting with continuous energy transfer equations. Basically, if reason, some of the reason is homogeneous by design, for example, we like to maintain it as homogeneous. And so it will be clear after several pages. If we are multi-grouping, the total cross-section, especially the total cross-section, becomes angle dependent. And we are just doing some uneasy stuff on this to make it angle independent. So here we are proposing some new way of doing this. And to do that, we need to introduce partial current discontinuity factor, PCDF here. And then it has to be found. In this talk, for the sake of time, I'll discuss the problem 2 and the problem 4. And then some conclusions. Everybody knows this, 255. So this is the transport equation. Everything is continuous. This is all the derivation is intuitively straightforward. So we don't have any question on this. But to solve this, especially in the past, deterministic methods, we do first come to multi-grouping of this transport equation. And if you do this multi-grouping, then this cross-section, if energy is condensed, then it becomes angle dependent. And later I will also show mention that if this is piecewise constant in space, this also becomes space dependent. Piecewise homogeneous region, if we multigroup it, this becomes space dependent also. So which is gives us trouble in applying numerical methods. So we like to get around of this. So this is what I mean. The total cross-section, because by definition, this ratio. So therefore, the result will be angle dependent and space dependent. Even if this is space independent, this ratio becomes space dependent. That's where it comes from. So especially, this has not been, the R dependence has not been paid attention too much in the literature. But this one, people paid attention. So so there are several methods, which is removal of this angle dependency by this or by this. These are in textbook. Lately generalized angle-dependency scheme, I forgot what it is, but this is relatively new, but still not satisfactory. There was also S2 type of collapsing, which we have been doing several years ago. This is not extendable to larger problems, multi-dimensions. So here, what I named it very fancy name, homogeneity and isotropy restoration. Total cross-section is angle dependent, but we like to be angle independent. So isotropy is restored, and homogeneity, if original reason is homogeneous, but multigrouping becomes space dependent, but we like to remove that. We like to maintain reason why this is homogeneous. And in doing that, we introduce PCDF to preserve reaction rate and K elevation rate. That's the bottom line of deriving an equivalent multigroup transport equations. Again, so this is the key page. So this is definition, multigrouping definition. So as I mentioned, this becomes R-dependent and angle-dependent. So what we do here, we introduce numerator and denominator. We do operate this for volume Bm, which means M region is less homogeneous, originally homogeneous in this case, and every angle. So we do this on top here and also denominator. So it is artificial thing, which make this material homogeneous angle independent. But we have to do something else to fix this. We do this operation for all other terms, for other cross sections. So if we do also on scattering cross section, we do this operation. It's a byproduct. The scattering moment, only zeroth moment remains. All higher order moments disappear, which is unexpected byproduct, which is very, very convenient. Similar thing for other cross sections. So this operation will be done by continuous energy Monte Carlo for a chosen problem, for unit problem which you are explaining. The right hand side is done by continuous energy Monte Carlo on a unit problem with general elemental boundary conditions. So for a chosen small problem, we do continuous Monte Carlo and evaluate this. Then these cross sections, multigroup sections, are coefficient in the derived multigroup transport equations. Okay, let's see. This is original transport equation. If we integrate over material reason and also angle, then the relative becomes this. This is angle independent. This is only first order moment, zeroth order moment, scattering cross section. This is already isotropy. So this can be recast. This is integral form, volume integration. This will be can be recast in differential form in space. So here is some jump, but so let's take an example. So this is like a unit cell, thin cell problem. So we consider some boundary conditions on this, in the type of albedo type of boundary conditions. On this, we like to have multigroup transport equations, preserving reaction rate on each region. So therefore, K will be also preserved from continuous energy Monte Carlo to the solution of derived multigroup transport equations. Then we are home. The result of multigroup transport equation will provide you the results from the continuous integral results. To do that, because of this term, to make this term and this term equal, we have to provide the discontinuities on the interface. On this, or if you the material interface. This is boundary condition for this unit cell problem. So then what is partial current discontinuity factor? suppose, let's take an example. We have four surfaces, surface 1, 2, 3, 4. So in this instance, we also consider four surfaces on this. 5, 6, 7, 8. This is a choice. We can reduce the region with the boundary, or we can even define the boundary. But this is, I think, this is convenient choice. So what we'll do is we have the boundary conditions. So we allow partial current discontinuity here, partial current discontinuity here, and here, and here, and so forth. In doing so, we can derive the multigroup transfer equation, preserving K and reaction rate. Reaction rate of this region, by allowing current, partial currents discontinuous. So this is the key step. And then the question is how to evaluate discontinuity factors. 1, 2, 3, 4, 5, 6, 7, 8 surfaces. In this choice, you may choose defined interfaces or more crude interfaces. But this is we think this is a good division. All right. Let's say two materials. This is outgoing, but we allow discontinuity. It's incoming from this, we allow discontinuity. So the question is we have to find discontinuity vectors here and here, all the material interface. In this case, four interfaces. Of course, this is partial current definition. So we allow discontinuity. So we have to find this discontinuity factor. But the reference will be from Monte Carlo continuous energy calculations. So the question is to find this. And if you write this in four discontinuity factors, this is the form. So this will be the reference, which is from Monte Carlo. This is the outgoing partial current from the result of solving derived multigroup transfer equation. So it's an implicit relationship. So we have to find this, which requires some kind of Newton method. So from continuous Monte Carlo calculations, we will have from the expression. Remember integration, the ratio of integration in previous pages, and net current from this. This is going to be net current is to be preserved, and reference net current and discontinuity factor, the relations like this. So this has to be found there in implicit form of nonlinear equations. So we find this by Newton's method, basically, until this reference net current is within the error bound of the result of this multigroup equations. So in this way, reaction rate and leakage, reaction rate in each region and leakage rate are equal to the result of Monte Carlo. So this is the basic flow chart. Now this F are appearing in a nonlinear form. So we found the JFNK method is very useful on this. Now F is positive ratio, so it's from 0 to, let's say, infinity. So it will be always, for positive numbers, it is useful to make this exponential transformation. To find, to make this very small. So this is basically JFNK iterative methods. So we'll see the effect of this JFK in the example problems. Okay, let's take an example. This is typical pin cell. On if your pin, this is the typical dimensions. And as I mentioned, the step one is you solve the boundary conditions given as albedos. Albedo not necessarily equal to 1. So this should represent the typical pin cell in your problem by these albedos. Albedos represent the environment where this pin cell sits in. So some pin cell will have a different environment. Then you have to repeat this for different albedos. So step one is continuous Monte Carlo. So J net, the reference is to be found. Generation of reason average multi-cross sections and net currents on reason interfaces. Remember the integration of the numerator and denominator. And PCDF, partial discrete vector, has to be found by iteration. And this result of deterministic calculation should be the same with the from the result of Monte Carlo. So the multi-group deterministic calculation in this study was done by a method of characteristics, MOC calculations. All right, this shows the 4 example problems. Here I'll focus on this. The albedo doesn't need to be 1, so that's why I chose this. Albedo is slightly different from 1. And there I'll show you another example, which is depression. Depression is coming out. So this is pressure. Right? So surface 1, 2, 3, 4. This is our application. This is the Monte Carlo continuous Monte Carlo conditions. Using this code, typical inactive cycles, inactive cycles, and so forth. Energy boundary is 0.6 electron volts, as typical for thermal reactors. This one thing. The number of groups is 2. This is again choice. So it should be what value of G is better may depend on the reactor. Fast reactor may be different from thermal reactor. But in this thermal reactor, so we chose 2. MOC calculations, 2 group MOC calculations. I think it's defined enough. Define the number of cells, the cell meshes, and angles, number of. Jasmine has done this long time ago. These are the error criteria. This is error criterion on fission source and K effective to match from the Monte Carlo result to multigroup results. So we make it quite tight. And also this iteration we used ostensibly 7 for net current should be satisfied within the ratio should be satisfied in the All right. These are this is the problem 2. Remember problem to have albedos are not equal to 1, slightly different from each surface. So on the pure reason, this is macroscopic. So group 1 and 2 are this. These are the unit. So this is the result of this calculations. As I mentioned, scattering is only zeroth of the moment survives, not any higher order moment. And these are the moderators. Okay, this problem too. So cross sections are generated. 2 group cross sections are generated. All right, this is then PCDF, partial current discontinuity factor. Not only multi-group cross sections, but also this PCDF is very important results. This again problem 2. Remember group 1 and 2. This is the F1 minus, and remember 1 is left surface, and 1, 2, 3, 4. Okay. So 1 and 2 is opposite. So they are not the same because the albedo condition is slightly different. So this is a boundary, and 5, 6, 7 is the internal interface between pure and moderate. So these are not symmetric because boundary conditions are not symmetric. And the choice to represent the environment of this pure P. All right, this shows K effective. Well, this shows also the other, but let's focus on problem 2. K effective, this is reference from Monte Carlo. With this, I guess, variance. This will be K effective from this multi-group equations, which is practically the same within 0.2 PCDF. So from this, we can say K is reproduced, and also reaction rate in each region. There are several reasons, right? The reaction rates are preserved. Otherwise, we cannot have this. How many iterations? These are fixed point iterations. These are the iterations for the nonlinear solvers. These are each nonlinear solver requires one MOC calculation. So this quite many 800 MOC calculations. But if you use JFNK, this is just simply a Newton method. If you use JFNK, it reduces to this, which is significantly reduced to the number of iterations. So this is very important, this operation. Yeah, we have also other problems. So similar results. It was K, right? This was the K. This was the K. What about reaction rate and reason average flux? Problem 2. The group 1 flux, the error is this, which is practically the same. And this is standard deviation because of multiple compared with this group 2. So they are all very, very accurate. Less than 0.1%. So we have done this for all other problems. It produces multigroup factor and the regional reaction rates. It produces of the continuous energy Monte Carlo results. Now, this is recent work. So we have applied this for in the case of depletion. As a simple-minded start, we divide, the depletion proton is built up near the surface and so forth. So we already know from other studies that there is a rim effect. So we further divide it inside of the pure rod into, I guess, 10 equi-thickness rings as a start. But later we'll notice that, maybe there is maybe not equal length, maybe equal volume division maybe there. So in this case, problem becomes quite large because there are many surfaces, regions and surfaces. So it will be very highly, the nonlinear equations you have to solve by JFNK is quite large. Depletion, we have seen this. Now, for example, this one, this is depletion of up to 500 full power days. I think this is range 238, which is like, this is the end of the pure rock. So deplete quite rapidly near the surface. So then plutonium, this is built up on the surface. So this is called, in the literature, it is called the rim effect in depletion. So because we chose the same thickness, this is what we have now. These are the conditions for the Monte Carlo calculations and MOC calculations, which is the typical specifications for this type of calculations. Now the result, the K effective of this problem, by Monte Carlo, or K effective is 0.98 with this variance. But from MOC calculations, by using MOC on multigroup with this PCDF, have this, which is the difference of this is less than 1 PCM, which is, you can say they are equivalent. Now, how many iterations? 3, because in this case, the JFNK is utilized. This shows the more the details of this result. I guess this is fast flux. This is a thermal flux. Fast flux. This is average. Average means this is beam-wise average flux. It's like this. It's like this. And this is variance in flux tally by Monte Carlo. Variance is like this. Now this is quite large. The students who worked on this, he used the collision estimator in the gap. There's very less number of collisions already there. So we should track that later on. We use track that. So then this will go down. And the red is the difference between from deterministic calculations to Monte Carlo. So these are the difference. The scale is here, which is percent. So we can say the reason why is the reaction rate, in this case flux is 3 over almost equivalent.